back.
Today's experimental math seminar speaker is Ali Unko, currently at Austria, Linz, and also at University of Bath in the UK, who will speak about reflecting on the modulo 9 Kanade-Russell conjectural identities. Thank you.
Yeah, thank you, Doron.
If you have a question, please unmute yourself and feel free to ask. Thank you.
Yes, perfect. Yeah, thank you, Doron, for introducing me. And yeah, thank you for giving me this spot to talk about this new exciting project that I finished with Vadim Zudelin. And there are many things to unfold here. So there's like this word, say, reflecting, whatever that means, I will explain. There's modulo 9, Kanade and Russell, who are they? What is conjectural? What is an identity? I will talk about them. And as you said, Doron, I am affiliated with University of Bath, as well as Johan Radon Institute at this time. And this is a great experience so far. Yeah. So
sorry, Ali, a little bit curious. Some of these conjectures have been solved a couple of years ago. So
yes.
They're still open ones?
Oh yeah, there are like still 5 open ones, and all the modulo 9 ones are still open. There are more
okay,
12 ones.
So those that have been solved. Yeah.
So I will mention them.
The ones that are still open. Thank you.
Yes, I will mention them as we go. Okay, so let's start with what these identities conjectures are about, and they're all in theory of partitions. So let me define a partition first. Okay, so a partition of a positive integer n for me is a finite list of decreasing or non-increasing natural numbers. So I don't need strict decreasing. And here's an example of the partitions of 5. So here are 7 partitions of 5. And as you can see, here is a list of non-increasing natural numbers that add up to 5. And when we are talking about partitions, we don't want to talk about them one by one. We want to group them in big groups, and one grouping would be the size of them. So here is the partitions of 5. But in general, again, we don't want to deal with just the partitions of 5. We want to deal with partitions of every number. So for that, I need to define a generating function for these objects. And that I define it this way. So given a sequence a sub n, the series a sub n q to the power n is the generating function for this sequence. That is how I'm defining that. So the exponent of q is keeping track of the sequence element, right? So if you were to take all the sets of all the partitions, and if you were to take all your partitions and group them with respect to their sizes, you would get what is called the partition number Pn, Qn, and you will see a list like that, such as this one. So 1, a partition of 0, that is the only conventional partition of 0, meaning that it's an empty list. There is 1q, one partition of 1, here it is, just one piece with 1 in it. There are 2 partitions of 2, 1, 1, and 2. And there are 5 partitions of 4. So these 5 elements here. So q to the 4 is keeping track of how many partitions of 4 there are. Okay, but yeah, great that we now have a definition for a generating function. We know what objects we would like to count or understand, but this open list is not doing much for us. So we want to see closed formulas so that we can actually maybe see some correspondences between partitions. And for that, I will define some objects. And these are the Q-polymer symbols. So AQ sub L is given by this L multiplications, 1 minus A, 1 minus AQ, 1 minus AQ, all the way to QL minus 1. And if I'm saying AQ sub infinity, it is just that L going to infinity, it's an infinite product. And if I have so many of them with the same base, same Q, I would put these Q polymers together. I would abuse the notation a little bit and write it as A1, A2, all the way to AQ base Q sub L. And that would be just the multiplication of these Q polymers. Okay. One more generating function. Oh yeah, so what these generating functions do is now with these, we can give interpretations of, we can give some substance to these generating functions that we saw as an open list before. So this product, 1 over Q sub n, can be interpreted as the generating function for the number of partitions with parts less than or equal to n. That sub-index over there is giving us the parts, the bound less than or equal to n. You can also interpret the same generating function, the 1 over QQN, as the generating function of the number of partitions with number of parts being less than or equal to n. Okay, another example. You can take minus QQ sub n, and that is the generating function for the number of partitions into distinct parts, all less than or equal to n. So again, that n is the bound. And one more thing that we will start seeing in a second is if you were to have a q to the a and a q to the b sub n, or minus qa minus qb sub n, that would mean a modulo b. And that n, the bound is going to change respective to that. So if you look at this, we pick an a between 1 and b, then these two products, 1 over qa base q to the b sub n, is the generating function for number of partitions into unrestricted partitions, where each part is less than or equal to b and minus 1 plus a. And if you were to look at the non-reciprocal one, the minus qa, this should be a q to the power b sub n, is the generating function for partitions into distinct, again, just like this one, but now the parts are not 1 modulo 1 as we see here, it is a modulo b. Okay, now we have some substance of the generating functions. We know how we do some interpretations. I will define one more generating function, which is the Q binomial coefficient. It is the generalization of the normal binomial coefficient, and these were the generalizations of factorials anyway. So this Q binomial coefficient can be interpreted as the generating function of number of partitions that fit in an m times n box. So now we're controlling both the number of parts and the size of the box with these Q binomial coefficients. Okay, these will be present in our formulas as we go by. But yeah, so there are these objects that we can interpret as generating functions, and we can use them to build up more complex structures so that we can understand, we can put some substance into a combinatorial theorem and carry that to the generating functions world and maybe see it as an algebraic equality. Okay, so from this point on, I will talk about the partition identities and what they would mean, what I'm talking about when I say a partition identity. And I call any two sets of partitions being equinumerous for every size, every positive integer n, a partition identity. So if you have two sets of partitions for any partition size n, and the count of these two sets are the same, not necessarily the partitions are the same, but if the counts are the same, I would call this a partition identity. So here's an example. Here's one of the most famous ones. For any integer n, the number of partitions of n into distinct parts is the same as the number of partitions of the same n into odd parts. So in one set, we're just taking partitions where none of the parts repeat, where all the parts are distinct, or you can think of it as all the parts of this partition differ by at least one, so that I introduced the difference conditions a little bit. And in the other set, you can have repetitions. You don't need the parts to be distinct at all. All you need is your parts needs to be odd. So on the one side, you have partitions with different parts. On the other side, you have partitions with some sort of congruence condition. And this is a common theme. We have a set of partitions with a difference condition on them, a different set of partitions with a congruence condition on them. And we call them, I would call these type of identities to be a difference congruence identity, partition identity. So here's an example. Let's look at partitions of 6. In the first set, if you look at partitions of 6 into distinct parts, you only have 4 of them. So 6, 5, 1, 4, 2, 3, 2, 1. You cannot make any other partition of 6 that doesn't have a repetition of parts. So that is coming from the first set. And there's another set where there are a lot of repetitions. These are the partitions of 6 into odd parts. And you can see that these two sets are equinumerous, but they're completely separate from each other. They're completely different from each other. Okay, so this is the combinatorial version of the Euler's theorem. And I talked about I talked about the generating functions, and I said we were talking about them to put some substance as generating functions to them. Here's the generating function version of it. So the number of partitions of n into distinct parts is generated by this Q Polynomial symbol. We have already seen it as an example. Minus Q sub n was partitions into distinct parts, where the parts were less than or equal to n. This time it is infinity, so that's bound on the largest part is gone. And on the other side, we have 1 modulo 2 parts. So this is the generating function for partitions, unrestricted partitions into 1 modulo 2 parts. And yeah, so there's a combinatorial theorem. There's a generating function version of that theorem, but most of the time, this generating function version of these theorems show up as a sum is equal to a product. And I will write it that way too. We don't need to write it this way. There's more than one ways of writing things. So let's write it that way. So you can interpret this left side as the generating function for the number of partitions of n into distinct parts. And that is equal to the generating function for the partitions into odd parts. And here I should say, and I will repeat myself, that we can make different interpretations of the sum and of the product, but the interpretation of the product usually is really simple. You look at the residue classes that you have. Here it is just q to the power 1, so you have only 1, and then you look at your modulus class, which is 2. So you say, I have partitions into 1 modulo 2 parts. Maybe we will have more than 1 residue classes in the next examples, but here it is just we have 1 modulo 2 parts. So whenever we have a congruence condition on a set, we already know the generating function for them. But I should say that, yeah, this one is not so hard to prove here, but usually jumping from the sum side of a generating function equality to the product side, tying this knot, showing this equality is really hard. Okay, let's look at the next example. And this is one of the real famous ones again. This is Rutgers identities. There are 2 of them. Let's take I to be 1, so we talk about just one of them. It says the number of partitions of n into non-consecutive parts, greater or equal to 1, parts being greater or equal to 1 doesn't matter for us now, is the same as the number of partitions of n into 1 or minus 1 mod 5 parts. So here we have non-consecutive parts. So the partitions, the parts of the partitions are at least 2 distant from each other now. And on the other side, we have partitions with a congruence condition. That is, you can have either 1 or 4 modulo 5 parts. And here the repetitions are allowed again on the second set. And we said the congruence conditions are also easy to understand when we have generating functions. So here is how you would write it as a generating function identity. Here's a sum that we can interpret as the number of partitions of n into non-consecutive parts, greater or equal than I. For I being 1, that goes away. And here is the congruence condition that q to the I, q to the 5 minus I modulo 5 sub infinity. And again, showing this equality is quite hard. And even if you know that this sum is equal to that, I mean, even if you're sure that this is that, it is really hard. Okay, so I gave 2 famous examples. Now I will give an example that is dear to my heart. It is Capparelli's first partition theorem. You do not need to worry about this. This is just to say that there are some difference conditions, more complicated difference conditions. And again, this is equal to some more complicated congruence conditions. And we have distinct, so we will not see reciprocal product here. But yeah, so although these partition theorems are quite rare, we know some number of them. But here, for this example, which George Andrews proved first, we didn't have a generating function version for a really long time. And Rutgers partition theorem came as a pair. There were 2 of them. Capparelli's partition theorem is the same way. So there is a secondary one. So you just change something to 2 here. The congruence conditions change to 2 again. And for me, I don't know why these things are coming in pairs or coming in triplets. But when these partition theorems appear, they appear in couples, they appear in pairs or triplets, and so on and so forth. But again, when this partition theorem was being proven, I apologize, the light is going off, but I will just keep on going. When this was proven, we didn't know the generating function version of these things. This was proven by finding a finite version of these objects where it satisfies some properties. We can talk about that later on. But we didn't know that some product type identity for these things. And in 2014, Shashank Kanade and Matthew Russell, I at least know Matthew Russell is in the audience. Yeah, so they experimentally found 6 different congruence type conjectural partition identities. So they did a big enumeration of partitions with difference conditions, created truncated series generating functions, and checked if they factor nicely. And if they factored nicely, if these truncated series factored nicely, they already knew the interpretation for these product, which was the congruence conditions. And this is how they found 6 difference conditions, 6 different congruence type conjectural identities. 4 of these identities were modulo 9 based, and 2 of them were modulo 12 based. And similar to Capparelli's theorem, the generating function counterparts of these conjectures were not known. Okay, well, and as I said, 4 of these 6 identities were modulo 9, and 2 were related to modulo 12. And Russell later presented one more modulo 9 identity in his PhD thesis. And in their later paper, Kanade and Russell extended their list of modulo 12 identities to 11 identities total. So I should note this here. This 11 identities total, they're all proven now. So modulo 12 identities are proven. The 7 of them were proven by Brinkman, Malberg, and Jennings-Schaefer. And then the remaining 4 was proven by, the name is escaping me. I am apologizing.
Rosengren.
Exactly, and it's not an easy name. That's why it's. Thank you, Russell. Thank you, Matthew. But yeah, the modulo 9 identities are still open to this day. But again, one key point was at this moment, the time of this discovery, their generating function counterparts were not known. So here's one of these identities, the number of partitions of something, something, a difference condition, more complicated, just as in the Capparelli's example. It is equal to some modulo 9 congruence condition. And I'm putting in equals with a question mark to say that this is still conjectural. And in 2018, in Andrews' 80th birthday conference, Kushingers and Kanade and Russell both independently announced that they actually found the generating function counterparts of these. And Kushingers found it through some combinatorial construction way. And I believe Matthew and Shashank found it through some computer experimentation. But they also later found some combinatorial meaning under that too. And they also found this generating function counterparts. They not only found the generating function counterparts for their conjectures, they also found generating function counterparts for Capparelli's identity, for example.
Ali, if I can just interrupt
Please.
here. If we go back to the previous slide, that's due, the generating functions, that's due solely to Khan, not to us, not to Shashank and myself. So
Okay, great.
Just want to give him the credit for that. Capparelli was independent between us and Khan, but
yeah, I was sure of that. I told you also found the generating function versions of your identities, but yeah, thank you for correcting me.
yeah, so Khan deserves the credit there.
Yeah, Khan deserves a lot of credit because one more thing, I should say that Khan knew about Capparelli's generating function counterpart in 2016. He actually showed me those, but I was too ignorant and too I couldn't understand the meaning, or I couldn't understand the value of those back then in 2016. And he later published that, and I mean, it became really what it is. Okay, yeah. So here is the generating function counterpart. of the Kanade-Russell, the first conjecture. So here's a double sum this time, but it's a sum after all. And it is, we are conjecturally thinking that it's equal to a product. And again, the product, the residue class is 1, 3, 6, 8. You would see them modulo 9 visibly in the product. And Kahn gave a combinatorial construction of how you would interpret these objects to give you the partition with the difference conditions that is expressed here. Okay. And yeah, there are 5 of these identities. There are 5 of these conjectural identities that I mentioned. So 4 in the initial paper from the Kanade-Russell, and the 5th one in Matthew's thesis. So you can write them like this. I believe I wrote the last one, but I mean, Kahn could have found it if only he knew that you had the 5th one. And I want to show you that the first 3 identities, first 3 products here are what we would call symmetric. So if you see 1 modulo 9, you also see 8 modulo 9. So it is +1 - 1 modulo 8. 3 + 3 - 3 modulo 9. Sorry, yeah, +2 - 2 modulo 9 + 3 - 3 modulo 9. And the last 2 are not symmetric. These are asymmetric identities asymmetric conjectural identities at the end. Yeah. So there is some difference in structure going on in that too that we don't fully understand yet. And as I was saying, yeah, Kahn and Matthew and Shashank also found generating function counterparts of Capparelli's identities. And as Matthew also confirmed that this part is true. So here's one of them. Here's the first Capparelli's identities, sum product version. And if you look at this Q factor, this is a proven theorem. But the only difference between the first Kanade-Russell conjecture and the first Capparelli's identity is that the factor 2. And it just makes it so much harder with that 2 not being there. I don't understand why. But these are 2 similar, these are really close by, but somehow Kanade-Russell conjecture is now, I think it is on its 7th year. It is like, it is open for 7 years. And yeah, this one was directly proven like many times over. Okay, so what can we do with these things? So now let me talk about what techniques we tried and what techniques have failed that not necessarily are in the paper that I talked about with, that I'm talking about right now, that I wrote with Vadim, but we tried many techniques. So one of the things that we could try was what Brinkman, Malberg, and Jenny Schaefer did. And that is they tried to guess a Q difference equation. They tried to guess some relation that a more general version of the generating function would satisfy, and then try to get to the product from that. So I will work on the Capparelli's cases just to compare Capparelli's case with the Kanade-Russell conjectures, okay? And Capparelli's case will time and time again show that it's much nicer in this situation. So what would you do? So you would take your generating function, you would try to make it bivariate, you just put another variable, like I'm just putting z n plus 2n, and then try to understand if this thing, the bivariate generating function, satisfies any sort of relation. And this statistic here is the number of parts in Kahn's construction. So this statistic is combinatorially meaningful. And if you look at this generating function with this extra z, you can easily just form an ansatz and solve it and see that it satisfies a Q difference equation of this form. So you see the original CZ, you see that Z Q cubed and Z Q6, Z Q9. So there's a shift, so if Z goes to Z Q cubed in this function, right? And this Q difference equation for the bivariate function also is equivalent to a recurrence relation for this coefficient, if you were to think of it as a formal power series for z to the k. And that recurrence relation is this. These are equivalent. And here, this is an order 3 recurrence relation. And you can see it here too. So the maximum power of z that you see in the coefficients becomes the order in the recurrences. So here I see z to the power 2z. There's z cubed here as the maximum power of z in this polynomial. So that reflects as a order 3 recurrence. But what Brigman, Malbrook, and Jennings-Schaefer did was they played this trick of, can we see a good substitution? Can we see a smart substitution so that we can do it? And maybe we can get away and drop the order of these recurrences. And here's a smart substitution. You can see that this term, 1 minus q6z, seems like it is a piece of a q-polyhammer symbol. So maybe it is a piece of that z q cube sub infinity. And then you switch your function and say, okay, I will assume that this z q cube infinity factors out, and let me talk about this new function gz, I mean with a lowercase z there. So once you do that substitution, the formal Q difference equation changes, and the recurrence, because that factor is no longer there anymore, the recurrence for the coefficients of the inside becomes an order 2 recurrence. Then you can try to do a substitution here. Here it seems like there is another piece of a q-polyhammer, and then carry it back to the Q difference equation. So you do this going back and forth game and try to drop the degrees as much as they can. And if you can drop it all the way, then you find a product, you carry that back and show that this sum is equal to a product. And z equals 1 case would be the identity that you're looking for. Okay, so this is the Capparelli's case. So you see that there are pieces in the Q difference equation as well as in the Q recurrences that kind of hint what the substitution should be. Let's look at the Kanade-Russell case. So here's the same thing. I am putting the same statistic, which is still the number of parts of the partitions that we construct. And this has to satisfy one of these Q difference equations due to the terms being holonomic. But if you were to go ahead and find it, and this was hard to find, if you were to go ahead and find it, you don't see such a nice structure once, and you don't see an obvious substitution. Right? This term doesn't seem like a piece of a q-polyhammer. This term doesn't seem like a piece of a q-polyhammer, and neither term looks like a cube or something like that. I don't see a way of proceeding from here. And the order of z here is z to the 6. So the recurrence, if I carry that there, would be an order 6 recurrence that I doubt that I would be able to solve. So this was a dot. This is not a way to prove it. And there's not a way that I know how to prove the Kanade-Russell conjectures anyway. You can try something else. You can be more experimental. You can just say, okay, can we satisfy a partial differential equation? Can I just tag along one more variable, for example? And then you see that the structure is actually quite, becomes really, compresses, and it becomes really nice. But we don't know the entire solution space for this. We tried, and we found at least one solution, for example. So here's this function fxy that satisfies this Q difference equation, and we proved it. But we don't have enough information to actually first span the solution space and then get the KR1, for example. So this was also not the way to prove it. And so another way to try is when we look back at the Capparelli's examples, as Kahn wrote it, as Kahn-Kurshingus wrote it, what I did with my former advisor, Alexander Berkovich, was we understood the combinatorial structure of these sum sides, and we already had finite versions of the product sides from a previous paper that we wrote. So we tried to find a finite version of the sum sides by imposing an extra condition on the partitions, the largest part being less than or equal to some capital N. And we tried to see if we can form these generating functions, if we can just find these generating functions and prove that they are indeed these finite finite generating functions with an extra bound. And these identities, the sum equal to product identities, become things like these. So those q-polyhammers that you would see in the denominator became Q binomials to impose that extra bound. And these right-hand sides, we already knew them from our previous paper. And this gave a direct proof of Capparelli's identity. So if you look at this, once you prove that identity, you take limit n, capital N goes to infinity. The left-hand side goes to the generating function of Kahn. The right-hand side goes to the product. And these were direct proofs of these identities. And this is not the only version. We have found two more finite versions of Capparelli's identities, which you can use to directly prove Capparelli's identities themselves. And we have found infinite families on top of them. So yeah, there is a lot of work that I did together with Alexander Berkovich on this. And yeah. So one thing that we could try is we knew that these sums are equal to products. So when I was talking to Vadim, we said, and I already knew the finite versions of these things. It was the same type of structure, so I already had them written up. So we said, can we just look at these functions and maybe try to do something with their finite versions? And these are generating functions for these partitions with difference conditions. I impose an extra bound on the largest part and turn these generating functions into these. And again, the last one is too messy. I mean, all of them are quite messy, and I understand that. And star means that it is one at a point that you wouldn't usually consider that to be one. But yeah, they look quite the same. So it is the same Q factor, and those Q polyhedrons turn into something else. Now, of course, this didn't prove the Kanade-Russell conjectures. I still call them conjectures. But this also gave us some more insight into structure of these objects. We looked at their recurrences. We looked at how we can play with them if they turn into each other, so on and so forth. And one thing that we thought about is what would happen? This is a polynomial. What would happen if we were to homogenize it and then just look at it from the other side? So take Q to 1 over Q, if we were to reflect it, so to say. And visually, what I mean is this. So if you were to take this polynomial, an qn, and it's a polynomial, and plot it as the n on the x-axis gives you the coefficient of an, these polynomials look like things like this. They are finite values, integers, of course, all of them. And this might indicate they're unimodal, but they're not, or palindromic, they're not. But this is just one polynomial. Then you look at the next polynomial. Then you look at the next polynomial, and you try to understand what would happen in the limit. Then you try to understand what the series is supposed to be in the infinity. And that series, we hope that is the product, right? That is the conjectural product part. So what we did is maybe we can't really understand what this is going to be, but we can start from the original one again, take Q equals 1 over Q, then normalize it so it's a polynomial again, and start looking at this sequence. So we look at the next one, and then try to understand where this series is going. Would it make any sense? So we kind of derailed from trying to solve the conjectures, but we tried to say, okay, what if Q goes to 1 over Q? Where would we go? And we started with the fourth Kanade-Russell conjecture because this was actually experimentally found by Ole Warnar. So he observed that if you were to take Q goes to 1 over Q and clear the denominators, then you have you need to be careful about the modulus. But when you take the limits, these reflected versions seems to be going to modulo 45 products. So the original Kanade-Russell conjectures were mod 9. You reflect them, clear the denominators. Now they seem to be going to modulo 45. We don't know why they are going to modulo 45, but there was some conjecture on that. And with the explicit generating functions that we already calculated, we were able to put some more substance in these conjectures. So here we could write them as a sum is equal to product conjecture. So, and all of these all of these conjectures of Kanade-Russell gave us
Excuse me,
two more.
Ali. So these
Yes.
are equivalent. The reflected versions are equivalent to the original versions.
I would like to say no. So I don't see how we would be able to prove, if we were to able to prove one of them, I don't know how we can carry it to the previous one. Because in the
So it's-
limit,
Yeah.
they become a product, but if only I had a version of the finite version of the right-hand side, then they would be equivalent. But I don't have a
Thank you.
finite version of any one of the products.
Oh, but they're beautiful new conjecture. That's great. Thank you.
So the joke here is we were trying to be a part of the solution. We were trying to solve the Kanade-Russell conjectures, but we became a part of the problem. We created two more conjectures from every Kanade-Russell conjecture. So this is the I4.
No offense to theorems. Conjectures are much more exciting than theorems. So-
Exactly. They're really exciting, and like these are really nice too. Yeah, thanks. So from I4, we were able to get two conjectures plus one theorem. We can prove that this sum side is equal to these two, the sum of these two sum sides. So but this is not showing that it's a product. Still, we don't have a product here. So from every conjecture, we get two more modulo 45 products. From every asymmetric conjecture, we were able to get two conjectures for sum is equal to a modulo 45 product, and a theorem where we say that this sum is equal to that plus that. So here's the Kanade-Russell fifth, which appeared in Matthew's thesis. And again, we found two more mod 45 products and the sum of them for the other case, and they look like that. There are two things equal to a product. There are two things equal to a product. These are conjectures. And the other ones, the symmetric cases, they're modular functions. They're modular forms, modular functions. So when we reflected the finite versions of them, I need to define this thing. It was a big search space. We tried it. We identified what in which modular space they live in. But when we finally found that and reflected everything, we found these conjectures. So you reflect one of those symmetric identities, and you end up getting a sum of three and only three. I mean, there can be more presentations, of course, but in minimum three modular functions. So here's one of the examples. So here's a reflected Kanade-Russell one conjecture. It is a modular function plus some factor modular function plus some factor modular function. And again, two conjectures coming out of them, one theorem. So it just goes as like two conjectures, then a theorem showing that the sum of these two things is another sum. And that can be proven by the Q binomial recurrences. Okay, so we created 10 more conjectures for people to try, and 5 more theorems just so they happen to be what they are. And now we're stuck again. I do not know how we can proceed from here, but please, you're welcome to try all of these. In the paper, you would also find the finite versions of these sum sides. And I already mentioned how you can find the finite versions of these sum sides. That you just look at the finite version, reflect it, and clear the denominators. But we have been talking about the Capparelli's identity over and over again, and showing that there are similarities and how the Capparelli's identity were so much nicer, so much easier to play with. And I want to finish with that if you were to reflect the finite version of Capparelli's identity, the finite version was due to me and Alexander Berkovich. If you were to reflect those finite versions and clear the denominators, you would see that, for example, the first Capparelli's identity here would turn to a modulo 48 product. And this one we can prove. Once again, even in the reflection, Capparelli's identity is much more easygoing, much more just, yeah, I don't want to say useful, but much easier than Kanade-Russell conjectures that we can actually prove that this sum is equal to a huge product of modulo 48. And yeah, with that, I actually want to end my talk. Yeah, thank you for your time. And yeah, this was about.
Thanks for fascinating conjectures. I really love these new conjectures. They are much more interesting than if you proved the old conjectures. We have plenty of time for questions. Any questions?
Before the questions, there's one more thing that I have not mentioned. This paper, I mean, two more things that I haven't mentioned. So this paper got accepted in seminal literature of Combinator. And the second thing is, this paper was dedicated to Doron's birthday. So happy birthday, Doron, Mazel Tov.
Thank you.
We hope we will write many more papers and dedicate them to your birthdays.
Thank you. It's a very good, it's a very good birthday present. So,
yes, exactly.
And as you know, Matthew was my PhD student. So it's so nice that so much interesting stuff came out of it. And those that conjectures were proved, that's the least interesting part. Getting new conjectures and all the insight and the reflection is really exciting. Any questions from the audience?
I have a question. Well, I have a comment and a question. I just would like to clarify something. Do you hear me?
Yes, I can.
So is this your trick with substitution, lowering the order of operator? It looks like the Lambertian substitution, right? So you have Q difference operator, and you actually, well, your first order operator is your product you are looking for, and you are lowering order is the Lambertian substitution, just like the Lambertian substitution in differential case.
Yes.
Right? So, and actually you are lucky if your Q difference operator factors in linear factors.
Yes.
And so this, if your annihilator factors in linear factors, then your expression being annihilated is the Lambertian expression, and there is you can actually try to build minimal completely factorable annihilator. Did you look at this? That's what my question. It's quite possible. So you have an operator of order 4, but you have annihilator which is also completely factorable, but smaller order that annihilates the same Q expression, and then maybe it's easier to handle lower order.
I didn't look at it directly. I assume that so when I was doing these experimental searches, I use Carson-Schneider's sigma package, which has a big portion and a huge, it is influenced hugely by the Lambertian solutions and everything. And I used holonomic functions as well from Christoph Kuchan. But the way that I actually found these identities, these Q difference equations, was that I tried to guess the minimal one. So I created an ansatz and tried to guess the minimal one. In that sense, when I get an Q difference equation that I prove later on, I believe that I'm getting the minimum, the lowest order one anyway. Maybe an iteration of that would factor in a nicer way. There's always that chance, but I really build up my search space to the point I hit a solution, then I just terminate. So experimentally, the way that I build up.
But there is difference between, but there is difference. Your minimal one can be not completely factorable.
Exactly, yeah. So,
and it's quite possible that a larger order will be completely factorable. And so you are looking at the Lambertian at the end, right?
So, yeah, exactly. And in that sense, that might be like iteration of this minimal one that doesn't factor. So I don't know that for sure. What I know is that when I look at this example, the next one, which is about the conjectures, the tools that were available to me, the packages that I mentioned, like sigma package from Carson-Schneider and holonomic functions package from Christoph Kuchan, they were not able to find this like easily. I needed to guide it to this so that I can prove it. In a sense, this object, because of this 1 and mod 3 structure, I don't know what it is, but it is so hard to get these things, even to observe these things. So, but you're completely right. I couldn't, and if you have any ideas, I would love to hear it, how to actually get these linearly factorable versions.
Sorry, I don't have idea, but I have another comment. You had your K and R upside down on slides further.
Yes.
And it's very disturbing. It's hard to read.
That is completely true. And I believe
It's only for stupid people. Smart people have no problem looking at it. It's a beautiful graphic.
Doron, I'm so glad that you stopped me, because I was going to say it is also distracting to me, but Vadim liked them and I like them in that sense too. But I mean, when I look at them, they look a little bit weird.
It's a great eye catcher.
Yeah, it is, exactly.
Thank you. Very nice talk. Thank you.
Thank you, thank you.
Ali, I have a quick question.
Please.
Is it possible to have a very continuous systematic search of Russell and Kanade, even more so, and look at all these double sums with q to the power quadratic and systematically look for interesting new conjectures systematically? Has anybody tried that?
So let me just say, I'm writing some things about them right now. So it is possible if you put in the time and electricity, and if you have the computer search, if you have the base, then you can find identities.
And one last quick question. Empirically, how far did you go to verify them? To 10,000 terms, or how many terms?
So these conjectures or other searches? Yeah, we went really, really far. So I would say at least like, I think I went to 5,000, like in all of them.
Okay, so that's an experimental proof. Good enough for me.
Yeah, I believe them. And once one of these conjectures crack, all of them are going to crack. But we're just waiting for that one thing.
Thanks so much. This ends the formal part of this talk. Thanks again. People are welcome to stay a few more minutes for informal questions to Ali.
Right.
Robert, please stop recording. Thank you.